Hi friends, I just wanted to show you the circuit that I've been working on, kind of a high-powered circuit, trying to use the resonance from the capacitor discharges to power this coil. This is a coil I made from all magnets. So you can see they're just magnets stacked next to each other, all so that they're facing north-south, north-south, so there's no opposition in this one. I'm going to build another one that has the opposition. And so it goes in through our spark gap here, which creates the basically the frequency for the discharge. And then here's our two outputs, and it's just regularly winded, all the same directions and everything. So I'm going to show you guys the amp reading, and then we're going to do the volt reading from each side, and I'll be able to show you our input power and our output power. That way you can, you know what's going on. So I'm going to show you there's where the power is at, 65 volts, 66 volts. We'll have our watts here and amps. So what we'll do is we'll turn it on. Okay, you see nothing's happening yet. We're running about 30 watts. There it goes, it jumps up. And we're just above our 65 mark. We're getting about 1.5 amps. And here, let's turn it up a little bit more. There we go. So 1.2 to 1.4 amps coming out. So let's switch it to our AC volts, and we'll tuck our lead in there, and with the other one overload. Overload. Let's turn it down a little bit. Maybe we can get a reading. Turn it down a little bit more. I was getting about 700 before. Now it doesn't want to read. Let's go to overload. Overload. So at least 1,000 volts at 1.2 amps. So that's about 1,000 watts. And we're using about 132 watts. So we'll do the amp reading again. Open line. Oh, let's see. Well, so looking about 6 amps there. Okay. And we're using about 3 amps. About almost 4 amps. 132 watts. You can see the wires just moving there. It's like got its own little gravitational deal going on. Bouncing back and forth. This one too. A lot of movement on the wire. Because it's sound. We're using sound resonance. You can even hear it. It's not the regular electricity coming through it. We're breaking up the regular electricity, and there's no ground. It's just going to one side and then to the other, and then we're using this to switch it back and forth at about 500 nanoseconds is what it said on the oscilloscope. And this just fills up with this electromotive force, or heaviside current, and it gets released as resonance, as sound. So with the magnetism in there in this core that can take a high frequency signal, because it's going to be high frequency energy in there, but it's being released at a low rate. So at a lower rate anyhow. So there it is. That's pretty much the concept I think Don Smith and some of these other guys were going for. I gotta have the high frequency core like Tom Bearden and his associates were saying. You know, they need 8 billion to figure that out back in the 70s or whenever it was they made that video, the promotional video. But yeah, there it is. So the next thing will just be we'll probably have to reduce these coils here to reduce the voltage, and that way we'll just get more amperage out of it. So yeah, we're not really using any of the voltage because there's no ground here. We're just using this phase conjugate wave to produce this resonant sound here. It's just a punch of etheric energy space, and it goes right through the crystal lattice structure of the material. That's why it's moving it so much, because it's actually interacting with the space around it instead of just inside the wire. So the space inside the wire is interacting with the space outside of the wire. Yeah, so that's pretty much would be like a full system to run a small room, you know, and we can get a more efficient high frequency transformer here, like in my other experiments. This one just has the the amperage capability. So it's actually a pretty good one for it's a microwave transformer, and I'm using a pure sine wave filter here. So what this does is it takes the AC current from your wall, which is I'm connected to the wall right now, and it takes it and it takes your current and your amperage. See the two coils there, current and amperage, and it puts them into phase. So it becomes a pure sine wave. That's what Don Smith was saying needed to happen before it got into the transformer, so that the diode, the switch, could do its job. So everything was imbalanced because you got both sides coming in here, and then it's turning on and off, on and off, and on and off. Here, we're just filling this up, and then we're discharging this. When this dielectric breaks down, the energy is able to jump across. From our demonstrations, we've been able to show that, let's see, that this electricity, it's not harmful. So I could leave this all day and it would never cause a fire. But you can see it does leave a small, almost like it's a rub burn. So this electricity is not hot, so I can run this all day without it getting warm. Actually, let's see how hot this gets. So that's about 100 degrees. 100 degrees. So mind you, there's this thing is wrapped with really small wire, a lot of high impedance, but this thing is able to put a large inductive kick of that heavy side, the back EMF, if you will. It's not a forward sine wave. It's a resonance. It's a pulsation of that sine wave in electromotive force, like electrostatics. So you can just see the crazy movement of the wire there. It's just going along. See the core of the transformer. The transformer is about 100 degrees. Capacitor's nice and cool. Let's see. Our diode's nice and cool. And we're just going along here. It's 1,000 watt, 1,000 plus watts. It's like probably about 1,200 watts coming out of here from the meter. So let's see over. There you go. So now we got about 700 volt, and you can see how you can listen how it speeds up because it gives it somewhere to go. 700 volt. Let's go on the other side. That one's too high. Oops. Let's reset it. Okay, then it starts freaking out the meter, I think. Once it goes too high, you gotta keep resetting it. So, here's, 700 times, what was it? Over here we had our amps. Let's check out our amps. So we got about, where are we at here? About we'll call it 4 amps. So 700 times 4, that's 2,700 watts. Right? It's 4 times 7, 24, 27, or 28. Anyways, so yeah, there you have it. Next thing we could do with this is put it into a rectifier, and then we could put it into a battery and then run the system.